All right, welcome everyone. So this is our 35th live stream geometry. Sorry I couldn't make it last week. And this week we're choosing problems from the China Math Olympiad. So we have me and 4 other people with us here so far. And something's up with my Zoom account, so I hope we don't get kicked off in 40 minutes. But if we do, that's why. So these problems, they look pretty challenging. I think they're probably harder than the ones on the last session, which we solved pretty quickly. And so with that, I'm going to share my screen. Hold on just a second. All right, can everyone see it? I'll assume it's a yes. All right, so here's the first problem. So we have a triangle ABC. This one looked really interesting. It's a little slow, but just a second. And we have a circle, and it meets the sides at 6 points. So it could be sort of any circle. I'm going to rename the points in just a second. So it intersects AB at D1 and D2. D1 and D2. BC at E1 and E2. So yeah, I like this problem. It's like a very generic configuration. And then we have points F1 and F2. And D1, let's see what it says. D1, E1, and D2, F2 intersect at L. So we have those two. And then E1, F1, and F2, E2 intersect at N, or M. So we draw those two. And then, so let me just draw those points in. So the first one was L. Did I do this right? Let me check. So we have D1, E1, and D2, F2 meet at L. E1, F1, and E2, F2 meet at M. And F1, D1, and F2. Wait, something's not right. I don't think this point is right. Hold on. Sorry, D1, E1, and D2. Oh, I think this should be D2. Wait. E1, F1, and and E2, D2. Sorry. So this segment is wrong. There we go. And then that's M. All right. And then we have, for the last one, F1, D1, and F2, E2 intersect at N. And we want to show did I do this right? So it looks like CL, BN, and AM. So L, D1 and D2. Oh, D1 and D2 are on BC. Okay. So I think I need to Yeah. Yeah, I messed up a little bit here.
Labeling is not important, I think. You can prove that AM, BN, and CL are concurrent.
Yeah, so I'll change the problem. So, AM, BN, and CL. All right. Let's check that it's actually true. Yes. And it's interesting because, yeah, whatever circle you choose, the problem's saying it's still true. So that's pretty interesting, I think.
Should we projective transform here?
What?
Should we consider a projective transform here?
I guess I'm not too sure what kind of projective, but yeah, it seems like it might be useful. Some kind of projective geometry. So maybe Desargues theorem or something like that. So, yeah, I'd like to use Desargues. I feel like that's my favorite way of showing things like this, but it doesn't look that easy. Maybe Pascal's theorem, because
Can you name the intersection of E1, D1, and P2, F2, EF, F2, E2?
F2, E2. So do you want to label this intersection point right here?
Yeah, no, it's not. D1, E1, and F2, E2.
D1, E1, and F2, E2? Okay, yeah. So extend those two.
This point is on AM.
AM,
Pascal.
That's by Pascal's, I'm guessing, right?
Yeah, that's right.
All right. Sorry. Check the chat. CL. Oh, that's what Julio was saying. Okay. D1, or maybe he's saying something. CL. Yes, Julio was saying something kind of similar. So maybe I should draw all three. And once I do that, maybe then it'll be Desargues theorem or something similar. So I'll draw that one. And let me draw the other one too. Right. Okay, so we have these three segments. So D, A, and M, F, B, and N, and E, C, and L. Let's see, can we use Desargues now? So that would mean, what would that mean? Or maybe there's a simpler way. I'm not sure. So we have triangles ABC and DEF. And we want to show their perspective. So there's a, It's interesting. Yeah, I don't know if there's a way to use Cheba's theorem or something like that. All right. 8 people here so far. Oops, sorry. Or maybe there's some other triangles. Like what about LMN and DEF? We could try showing that those are perspective. I wonder if LMN is similar to DEF. In fact, I wonder if MN is parallel to DF. I feel like that might be too good to be true. Like is LN, no, there's no way LN is parallel to EF. Yeah. But yeah, this definitely looks like some kind of projective thing. I don't know if maybe we could use cross ratios. Let's see. So we have triangle. This would be, is LN parallel to BE? I don't think that could be. No. Maybe trig Cheba or trig Cheba. I try to avoid trig, but maybe that'll give us an idea. You can prove for two chords intersecting the circle as diameters. So what, like, are you saying E1, E2 would be a diameter and D1, D2 would be a diameter or something like that?
No, I meant that you could take D1, F1 and D2, F2 as diameters and then take a projective transform, sending their intersection to the center of the circle. And if you can prove the problem there, the problem still holds here.
Okay. So you can kind of do, because I guess projective transformations preserve concurrency and collinearity. So you're saying
Yes,
you
yes.
could make D1 F1 and D2 F2 diameters, right? Is
Yes.
what you're saying. All right.
Yes. Yes.
Let me think about that a little bit. So then they would intersect each other. So then A, I guess, would be inside the circle instead of outside the circle. Let me see if there's a way without having to do that. I guess I'll kind of keep that in mind, that that's always possible. I wonder if there's a better way of using Desargues. What if we use Desargues on like triangles ALN? Not. Let me think for a sec. I was thinking, I wonder what the circumcircle of LMN is. I don't think that does anything. I don't think it actually passes through this point right here. No. We shouldn't think about ABC. We have a circle and 6 points on it. Okay, yeah, so it's almost like we don't really need the points A, B, and C. Yeah, no, I agree. Let me hide some of them. Let me hide, let's see. It's like that, right? There we go. Okay. So we have 6 points on a circle and they intersect in this way. This is interesting. like maybe what I could do is like I could label this point right here. Oops, should be a gray point. I think I might need to hide one more. But anyways, I'll just leave it as blue for right now. Basically, we want to show. Oh no, that wouldn't work. Right, we got one more person joining. Got a good number of people here. Thanks for joining. Let's see, what time is it? Sorry. It's 11:30. Spend a little bit more on this problem. Okay, so for whoever just joined, I just hid points A, B, and C because we discovered a little bit more about the problem. Maybe it's just Pascal's theorem somehow. So can we use Pascal's theorem any more times? Let me hide these three for now. So that's what we want to show concurs. But can we use Pascal's again to show that is Fn and another point collinear? So let's see. So I'm bad at this, but F2, so those two intersect at F. F1E2 and B1F1 intersects at N. What if we drew, for example, I wonder if we could apply Pascal's another time. So if I drew these two, for example, oh, I don't think the intersection point, no, it would be collinear with this point right here. Can we get F and N to be collinear with some other point using Pascal's theorem? What about if we let D1, D2 intersect E1, E2? Oh, but I think that's B. Yeah, okay. So hold on a second. So I think, so L and N, I think are collinear with this point, right? No, what did I do wrong? It's hard. Could we try to use Cheva? What happens if we try to use Cheva? So, for example, if we draw this, can we say anything about, I don't want to make it look like they intersect on the circle. But for example, if we call this point G, can we say anything about FG over GE? Maybe we could use Menelaus to find that ratio. I'm not sure. I'm not sure about that. But yeah, the idea of are E and F collinear with some other point?
Yes, D and F are collinear with D1, D2 cut F1, E2.
Ah, okay. Wait, so D1, D2 intersect F1, E2? It's like that. I wonder if those almost look parallel, but I don't think they are. It is A. I guess I was thinking, are those parallel? No, they're not parallel. Okay. Maybe we could even use
That point is collinear with D and F, but I don't think it is of any use.
Oh, okay. That's by Desargues, I think, right? So Fn and A are collinear, and Fd and that point are collinear. What was I just thinking? I had an idea. Right, 1 second. Or you know what? We could get rid of L, N, and M. We could just try to show, what if instead we kept A, B, and C, but got rid of L, M, and N? I kind of like that. Let's try that. So yeah, we really don't need L, M, and N. But we could keep A, B, and C. So that's like a different way of thinking about it. Yeah. Maybe it's equivalent. I'm not sure. So then we don't need this segment. Well, I guess we do because we need to define E, F, and D. This is tricky. I'll spend like 10 more minutes on this, then maybe we can move on to the next one. Can we use Ricard's theorem in any way? So yeah, maybe we should add some more points, like
Maybe we should add some more tangents and then try to use Brocard's.
okay. So like so I guess you said tangents. Let me see something. So yeah, like this point right here. Yeah, I'm not sure. I'm trying to think how useful Ricard's theorem would be. Let's see. So one way, this is kind of weird, but we could, I'm trying to use the SARGs. But yeah, I don't think it's gonna work out too great. I'm just thinking how to use Bricards. I'm not sure if it's that easy. Maybe after intersecting FB and CE, we can use Menelaus. So I'm guessing you mean Menelaus on, or I'll try that. Yeah, so we have those two. And we want to show that DA and G are collinear. All right, let's go to the next one and see if we can figure this out later. All right. So this problem looks interesting. It's one of the problems with O and I in it. So we have O is the circumcenter and I is the incenter. Oh, did you figure out how to do how to do it? So I'll go back. Let's see. So by Pascal, so NM. Okay. All right, let's try it out. So, so yeah, you didn't use D, E, and F in your solution, I don't think. You just used N, M, and L. So that means I can hide D, E, and F. All right.
I think you can delete.
Yeah, I could probably delete instead of hiding. You're right. Delete.
Hello, Michael.
Hey, Feng. Thanks for joining.
Yeah. Okay. I have some problems. So I joined us kind of late. Yeah.
But, oh, don't worry about it. It's fine.
Okay.
But yeah, we're glad you're here. So yeah, so this is still the first problem. It was a tricky one, but I think one of the people, Rue83, just figured it out. Oops. Oh, yeah, I'm gonna have to redraw some stuff here.
If you deleted E first, it would be deleted, but that's okay.
It would have made it easier.
If you delete E first, it would be disappeared.
So it was like the order, yeah, because I didn't delete D first. All right, so I think this will work for now. So So we use Pascal's. So NM, D2F1, and BC concur. Are you sure? Are you sure? So Ru 83. Oh, LN. Okay, LN, D2F1, and BC concur. All right.
Yeah, we can hear you.
All right. So I'm going to go back to sharing my screen. All right. So, okay. So I'll check out the comments for that problem. Hold on just a sec. So, okay. So BC, I lost all the previous chat. But I think the idea was we use Pascal's to show that LN, D2F1, and BC are concurrent. And then we can finish by using Desargues. I think that was what Ru was saying. So and once we know that, what triangle do we use Desargues on once we know that? LMN and ABC. Yeah, interesting. Okay, so you'd need to do it for all three pairs, basically. So that is a tricky way of doing it. Okay, so basically we would draw these 3 points and then we would show those are collinear by Pascal, and then we would use Desargues, and that would solve the problem. That's an awesome solution. I really like it. Let me change the diagram a little bit so that it all. Let me see if I can get it all to fit on one diagram. Let's see. Yeah, it's hard to get all 3 of those points to all fit. But I really like that solution. That's really smart. Something like that. And then I'll shrink it a little bit. And I want to be able to see this other point. There we go. That looks good. All right. Okay. So I'm going to draw everything that we need. And let me hide a bunch of stuff. My bad. I don't know what just happened here. Yeah, I don't think we need D, E, and F, right? All right, so that's how you get that those three are collinear before using Desargues, right? So let's see, I don't want that line, and I don't want that line. All right. So we have those three are collinear. That and this. Okay. So let me move the diagram to the right just to make more room. Okay, so by Pascal's theorem, BC, LN, and BC, LN, and D2F1 are collinear at E. At some point I'll just say at a point E. And then I'll just say we can define H and G similarly. And by Pascal's theorem, E, H, and G are collinear. So, okay, so on E2, E1, F2, F1, V2, V1, we have E, H, and G are collinear. And now we can use the converse of Desargues. So by the converse of Desargues' theorem on triangle ABC and triangle LMN. That means AM, BN, and CL are concurrent. Awesome. I love the solution. We use Pascal's a bunch of times and then Desargues. That's very cool. All right, so let's move on to the next problem. So let O and I be the circumcenter and incenter. Okay, let me maximize this. So the circumcenter, I'll do this. So O is the center of that circle. And then we draw the in circle. And I is the center of B. All right, now I can hide this. Okay. And then B, E, and F are the points of tangent C. Whoops. Just. Didn't mean to draw that. Okay. Let me delete that. Okay. So let's draw D, E, and F. And FD meets CA at P. So we want to draw FD and ED and see where they meet those two sides. Oh, I forgot to draw the in center. Sorry. Where's the end circle? I don't see it. Oh, center of D. So I is the center of B. There we go. And let's see if we can make a diagram here. That looks better. That looks better. Okay, so these are going to be M and N. This is P. And this is Q. And then M is the midpoint of PE. And N is the midpoint of QF. It's a really weird configuration. And we want to show that OI is perpendicular to MN. That's M. That's N. And that's the problem. All right. Is MN, no, MN is not parallel to PQ, I'm pretty sure. Or is it? Let me just make sure that's not the case. Is MN, yeah, there's no way.
Michael, I have a solution for this.
Okay.
Yeah, it kind of, yeah. Let's say that P, E, A, C is harmonic, right?
What's harmonic?
P, E, A, C.
Oh, PEAC. Okay. So yeah, those are harmonic. That's a harmonic conjugation.
Yeah. So that ME square is equal to MA times MC.
Mm-hmm.
Yeah.
Okay.
So yeah, M have the same power to the O, the circumcircle and the incircle, right?
Mm-hmm.
Same with the M. So yeah, IO is perpendicular to MN.
Oh, because you can then, because then MI squared minus, or MO squared, So it has the same power with respect to both the in circle and, so that's actually a very quick solution.
Yeah.
Interesting. So I like it. That's very creative. All right. So the first one took us a while, but this one we solved really quickly. I'll say, so since AD, BE, and CF concur, for example, by Cheva, then that means that that means A, C, E, and P are in harmonic conjugation. And A, B, F, and Q are in harmonic conjugation. And so by a well-known lemma, so I've used this on our channel a bunch of times now. So then we have ME squared equals MA times MC. And similarly, I think it's NF squared is NA times NB. All right. And so basically that means M has the same power with respect to both the in circle and the circumcircle. So MO squared minus yeah, I'm just trying to think how to, Mn is the radical axis of them. Oh yeah, okay, that's even better. Yeah, I was making it too hard. So M and N have the same powers with respect to both circles. And that means that Mn is the radical axis of the two circles. And so that means that Mn is perpendicular to OI. All right. And now I will move on to the next problem. And yeah, I'm sorry if my computer ends up screwing up in another 40 minutes. Just, yeah, letting you guys know in advance. All right, so now we are on the third problem. This one looked kind of interesting. So we have a triangle ABC where AB is greater than AC. Oh, whoops. But yeah, next session, I'll definitely fix it so that my computer doesn't keep doing that. I'm not sure why it did it this session. So we draw the angle bisector and it meets BC at a point D. And then P is a point so that A is between P and D. So like that. And then I draw the circumcircles of ABD and ACD. And I draw the tangents from P to those two circles. So P lies on the radical axis of those two circles. So it's going to have the same, the tangents are going to be the same length, right? So this is Q. And this is R. And draws a little bit more tangents than I want. Okay. CQ meets BR at K. So let me make it so it doesn't look like it lies on the circle. CQ meets BR at K. The line parallel to BC passing through K. So we see, where does it meet QD, AD, and RD? Let me just move the diagram just a little bit so it doesn't. What if I move point P? Does that makes, I kind of like that. So, oh no, we don't want it to intersect QD really close to the circle. QD, that looks good. So QD, AD, and RD at E, EL, and F. Okay. This is L, this is F. And we want to show that EL is equal, whoops, what just happened there? EL, we want this to be F, and we want to show that EL is equal to KF. All right. Okay. Which is the same as saying EK is equal to LF, of course. So yeah, so we know PQ is equal to PR. Let's see. Is DL the angle bisector of EDF? That's very possible. Let's see. Kind of does look that way, doesn't it? I think they're very close in this figure, but I don't think so. Not, let's see, if I...
L may be the encircle tangency point.
Sorry, what did you say?
L can be the encircle tangency point. Encircle of DEF.
Okay, so draw the end circle of DEF. And then I'm going to check what, actually, let me just check that really quick. QRBC, is that cyclic? Yeah, I think it is, or at least it looks like it. Is that, okay, yeah, I'll think about that later, but that's a good, okay, so now I'm going to draw the end circle of DEF. Oops. And were you wondering if L was the tangency point?
Yeah.
I don't think it is. No. All right. What's that? Yeah, is it obvious that QRBC is cyclic? Sorry. I wonder if that's like, can we use, I wonder if there's a way to like use Pappas or something. So maybe we could try to show that the cross ratio ELF infinity is the same as the cross ratio FKE infinity. EQK is equal to KRF. Why is that? Oh, that can be proved after. Okay. So yeah, like what if we take EL and F and we ELF infinity and we project it through D onto, well, if we projected it,
We don't have any midpoint.
So yeah, we would need like this point right here, right? So we'd have to see where DR meets. I guess what I'm saying is we could show that ELF infinity is the same as FKE infinity, if that makes sense.
Yeah, it can be possible.
So yeah, I guess you don't need a midpoint for that. But yeah, how would we get FKE? That doesn't seem that easy. So yeah, if we show that BCQR is cyclic, QRBC is cyclic, oh, but P doesn't lie on the circle. I wonder if QREF is cyclic. Huh, yeah, that was a good guess. Yeah, it looks like QREF is cyclic. And maybe that's just an angle chase, I'm not sure, but so if QREF is cyclic and PQ equals PR, Is QLPE cyclic? That would be interesting. No. Is triangle? No. I thought maybe I saw some congruent triangles, but no, I don't think so.
Hi.
Hello?
Do you have my sound?
Oh yeah, I can hear you.
I think that for proving QRBC is cyclic, we have to prove that the intersection of QB and RC lies on the radical axis of these two circles, ADC and ABD.
Yeah, so you're saying you want to show that QB, RC...
For proving that we can use Cheva. Yeah.
Okay, Chavez theorem?
Yes, I think that we can prove it by Cheva, and we have some angles. We can use it by, prove it by Cheva. And after that, I think that if you label where QB intersect RC, that will be good. That won't be...
I wonder if we can also do it using Desargues. So basically, let me think about how we might do that using Desargues theorem. So if we let... Yeah, that might be a little tricky using Desargues theorem, but you think maybe Cheva we can do it with that?
Yes, I think that Cheva can help here.
Okay. Let's see.
Because AD is an angle bisector, and we have one of the angles cancel each other. We need to calculate just two angles.
So yeah, so we'd have these two. Okay, so maybe define the intersection of BQ and CR, and then show that AB passes through it, in other words. All right. Let me think about that for a second. You know what? I'm trying to use Desargues, and if we draw PB and PC, does PB intersect that on the circle? I think that's a coincidence, but maybe yeah, I'm pretty sure that's a coincidence. Okay, so if we draw PB and PC, so we would have this point, and one other point. So BQR and PBC. Oh, I think that would be tricky. Okay. But you think by Cheva. So I'll draw. Yeah, PQ is equal to PR. Maybe I'll just shrink this a little bit, just so that we can see the intersection. Yeah, P and A have to be kind of close together. What if I make it like a white? Yeah, there we go. That's better. It's hard to make a good diagram, but I'll just shrink it a little bit. Something like that. So we want to show that those are collinear, and then it would follow that QBRC is cyclic. Can we show QREF is cyclic in a simpler way? Let's see. So showing QREF is cyclic, that's the same as showing angle RQD equals angle RDC. So I think that's the same as showing that if you draw the circumcircle of QRD, it's tangent to BC at B. Let's see. Yeah, can we show that? Can we show that QRD is tangent to BC at B? That would be equivalent to showing that. So PQ, okay, so let's see, this is a circumcircle QRD. Let me try something for just a second. I don't know if that does very much. All right. Yeah, this diagram doesn't look that great because it looks like P lies on the circle when it doesn't have to. QBRC and QREF. Okay. And yes. All right. So yeah, let's see. Is there a way to prove that those concur? We could also try to prove that QR intersects BC at the harmonic conjugate of D. And that would prove that those concur. Now, actually, I kind of like that. I've been wanting to draw QR for a while, so let's see. Because then we could use that PQR as isosceles. Okay. Why is that blue? There we go. I feel like point G might be useful.
GA is perpendicular to AD then, if it's harmonic conjugate.
Or we want to show that BC, D, and G are in harmonic conjugation, right?
If that's true, then BA and AG are perpendicular.
BAO.
Oh, it's not okay.
Oh, but GA is tangent to the certain circle bit. Oh, okay. No worries. Yeah, you're right. Okay. All right, should I delete point G then, or should I leave it there? Just leave it there for now.
Excuse me.
Oh, sorry, were you going to say something?
Yeah, I think that for proving that Q, B, AD, and RC are concurrent, we can use Cheva and calculate some angles. We just need to prove that sine of QBD,
Sine QBD?
QBA over sine of QB, yes, over sine of QBA times sine of RCD over RCA is 1. And we have QBA, which is equal to PQA, because of PQ is tangent to the circumcircle.
Okay.
And we have RC, we have RC, same like this. And we have QBD is equal to QAP, and we have RCD is equal to PAR, and because PQ is equal to PR, it is easily concluded that PQ, RQ, BC is cyclic because they're concurrent with AD by Cheva.
Okay, let me try to write this out a little bit. Okay, so in order to use trig-Cheva, should I first label the intersection of BQ and CR? So I guess what triangle are we using trig-Cheva on? So
I guess we use trig-Cheva on ABC, right?
on what triangle?
On ABC. We use
on ABC. Okay, so basically we want to show that
yes,
sine.
ABC will conclude that. ABC.
Okay, So we just need to show kind of that sine. I think sine QBD over sine ABD is sine RCD over sine ACD. Is that kind of what you were thinking? I think that's what you were thinking, yeah, or that I think that's what you said. So we have
Yes, and because PQ.
So angle ABD is equal to angle AQD. Oh, Sardar, did you see? So AR over RD equals AQ over QD proves it. Okay, so
Prove the angle ratios are equal. We can use similar triangles.
so what triangles are similar?
We will use that AR over RD equals to PR over PD.
AR over RD is PR over PD. Interesting. So we have AR over RD is equal to PR over PD, which is equal to AQ over QD. And so from there,
we will write sine law in ARD
okay.
and AQD.
Okay, so sine this over AR is equal to sine that over AD. I feel like there's probably a way to do this without trig, but let's see. So AR over RD is sine of ADR over sine of ARD.
DAR.
DAR, sorry. And which is an ARD is the same as
ADR is ACR and DAR is RCD.
okay, ADR is PRA. And then DAR, well, let's see, what is DAR?
No, it's not PRA.
It's not PRA, ADR.
It's ACR. Better. ACR is better.
But wait, but angle ADR isn't the same as angle PCR, right?
It's equal, but we don't need that.
So AR over RD. Oh, okay. AR over RD. Are you saying ADR is ACR? Okay. All right. And then so we have that. And then similarly, we have AQ over QD. So that would be sine of ABQ over sine of DBQ. And so by Trigg-Cheva, and then it's obvious that angle BAP equals angle CAP. Sine of CAP. So by Trigg-Cheva, BQ, DA, and CR concur. Okay, so Hakan just asked, could we apply Pascal to RRCADA? Interesting. RR. Yeah, I'm not sure about that. If you can figure out a way to make that work, yeah, let me know. So I'm going to draw this intersection point up here. Sorry, the problem's overlapping a little bit. So they concur at a point H, and then from there we can show the cyclic quads. Okay.
I think just by easy angle chase again, HQAR or concyclic.
HQAR. Okay.
Yeah.
All right, let's see. So we have, and maybe that's just Meckel's theorem, right? Yeah, we could just say by Meckel's theorem, HQAR is cyclic. So we have PQ equals PR.
Yeah, it's pivot or pivot theorem, one of them.
A what?
Pivot or pivot. I'm not sure how to spell it.
Okay, so it proves that AP and the intersection of AP and RC are collinear. I think you should have said that BQ. You're right. Yes, it should be BQDA and CR. Good call. So 1 sec. Sorry, 1 second, guys. So wait, were you saying that Pascal's could also have showed that these concur, or you realized that it didn't work? Oh, okay. All right, so once we know this, then we could then show that QRBC is cyclic by power of a point. So yeah, we have a lot of cyclic quadrilaterals. I'll just draw both of them for now. But yeah, this is just power of a point. And this one is Meckel's theorem. Okay, so we want to show EL is equal to KF. Let me check how we're doing on time. It's not even 1 yet, or it's not even, so yeah, we have about an hour, 15 minutes. All right. So yeah, there's that last step of showing EL is equal to KF. I feel like we're pretty close. Yeah, how do we use that PQ is equal to PR? Yeah, I want to draw that circle, but I don't think it does very much. Let's see. Can we show, okay, yeah, I think this, yeah, the circumcircle of QRD should be tangent to BC at D. I don't think the proof of that would be too hard. And from there, are QEK and BFL congruent? Let's see. Sorry about that. So that angle is 96.91. And for DFL, I forgot, is it clockwise or counterclockwise that this does it? I always do the wrong one. Okay. I have to click D, then L, then F. E, L, F. No, they're not congruent. So what if I labeled this point right there? So it's I. And then, so if we project ELF infinity through D onto this circle, we would get DQRI, assuming that that's tangent, which I think we could prove. And if we project, it's hard to project FK and E. But if we project FK and E through R, huh. I'm not sure. So yeah, how do we show, yeah, EL equals KF. So yeah, L and K are defined pretty differently. So there's some kind of homophily we can do. So yeah, L isn't the tangency point of the incircle of DEF, but maybe it's for a different point, it's the tangent C. I don't know. Let's see. Yeah, what is the best way to show EL is equal to KF? I'm not sure what theorem we would use for that. So we know PR is equal to PQ. Can we use that somehow? Let's see. Maybe QREF being cyclic. Oh yeah, I feel like we really should use that. So QREF being cyclic and QEK equals KRF. I'm sorry, EQK equals KRF. Yeah. Yeah, if we know EQK equals KRF, I feel like, yeah, that would probably help a good amount, like you're saying.
Is A on the perpendicular bisector of EF?
Let me check. But yeah, basically, we want to show that L and K have the same power with respect to that circle, right? That would solve the problem. No, it doesn't look like A is on the perpendicular bisector. So yeah, can we calculate the power of L with respect to that circle and then the power of K and show that they're the same? That doesn't seem that easy. I don't think we know it, but
We
yeah,
do, we proved it.
It's not hard to prove. Yeah, I don't think it's hard to prove because angle EFB is angle FBG is RDG, which is RQD. Yeah, because this is tangent. I don't think it's hard to prove. So yeah. So I think it's not hard to show that BC is tangent at B. And so basically, if we want to show that QREF is cyclic, we have angle EFB is angle FBG is angle RDG, which is equal to angle RQD. And I think that does it. But first we need that the circle QRD is tangent. Is that easy to see actually? We would want to prove that G does not depend on P. Oh, is that true? G doesn't depend on P? Interesting. I did not realize that.
Actually, if we prove that AG is tangent to the circumcircle of ABC, we can prove that the circumcircle of QDR is tangent to BC.
QDR, okay, yeah. So, and I think that would also mean GA is tangent. So Let me draw that circle through A, B, and C. Yeah, so I think those two circles are also tangent. There's a lot sort of going on here. And then by the radical axis theorem, those three would concur. Do we use a homothety to show? Do you guys want to move on to the next problem and then come back to this later?